Okay, you're at the back. Group B. Group C. Group D. And Group E.
Yes.
So, sorry, what is this? 1, 2, 3 people, not groups. Okay, so the first one to get this right is
Yes. Karthik and Eddie.
John. Would you like to join me?
Karthik, you are the same group as me.
Okay. That would make that up to 5.
Yes.
And sorry, Group E, yes, I meant sorry. Yeah, Group E, who only had 4 in it, now have 5 with John joining them. And you two guys for a moment have to begin the nucleus of a new group that I'm going to call F. Yes, I'm going to call this group F. Alright? Now it might be that we get 5 people, it depends on if some of these ghosts materialise into real human beings. We might get 5, but if we don't, then I may have to change things a little bit. But for the moment, you form the group. Right, we've got group F.
Yes.
So it's Joby and Cardi. Alright, so just to remind ourselves what we're doing, you may have forgotten during that process of trying to get the group sorted. Sorry. Is there something you want to tell me? Okay, so we're going to work in these groups from now on, okay? And just to remind ourselves what we're going to be talking about, or what we're going to be dealing with, just to remind you of the solenoid operated piston pump. Have you had a chance to look in the web yet and see examples of this? I did encourage you strongly, didn't I? Yes, there's a good guy in the back. Right, you've passed, you can go home now. Right, so we're going to work on this. Question?
Actually, yesterday I tried to look onto this pump online. I couldn't get this design or this model of the pump on this website. Most probably this is the old design of the pump. So on the website,
Yes.
new.
It's new.
Yeah, there are new design of the pumps over there, but not this particular type of pump.
Oh, that's a shame, isn't it? But at least you've got a new one to look at. Right? That could almost be deliberate, couldn't it? So, we're going to be working with this particular concept, and what we've got to do, as I've said, is to try and design a product like this that's capable of producing 0.5 litres per minute nominal output. Now, we also want to do it between 0.45 and 0.55. These are the limits that we want to operate within. So we've got to make sure that we can design a product that will do that, that will consistently produce that. But the question is, as I mentioned on Thursday, what are the variables? What are all the things that could influence that output? Now, we've obviously got fluid coming in, and we've got the fluid coming out. But for that to work, as I pointed out, certain things have to operate correctly. For example, for the volume of output to be correct, then the diameter of the piston that's in here, this is a piston, the diameter of that and the amount it moves has to be controlled every time it moves. And if it's moving 20 times per second, say, if it's working at 20 Hertz, if it's moving back and forward 20 times a second, how do we know that every time it moves the same amount? It could be that it moves, say it's 10 millimeters, one stroke, one time. It might move 10.0001 the next stroke, or 9.9999 the next one. We don't know for sure, unless we design it so we control that output. That's the only way that we'll make this accurate. But of course the question is, how do we do that? How do we know what dimensions to put on it? How do we know what control to put on it? Right? That's going to be important for us. Similarly, we know that the springs that control this themselves have to be of the right quality so that they will, every time, 20 times a second, remember, maybe more. Every time it moves, it has to move and control this exactly in the right way every time. Or at least within the limits that we've set for this. Now I've given you these target limits. Can we even begin to meet them? Yeah, I've set you a target, but maybe it's physically impossible. We don't know until we start to investigate this and to find out what's possible, what can be controlled, and to what extent it can be controlled. If you don't know that, you can't tell me if that output that I've given you is even practical. Do you agree? So you have to investigate, you have to find out what do we need to do to make that happen. So it seems like a fairly simple process, but it isn't, because of all the interactions that we're going to get in this process. All right? So that's just to remind us what we're going to do, and for the benefit of the people who have just joined us. We've got to redesign this and control all these parameters such that we get every time the right output from this particular pump. Now, we discussed on Thursday that we've got a solenoid round here with just a coil of copper wire, and then basically the piston in here is a ferrous material, and every time this is energised, the core moves backwards and forwards and is returned back into the core by the spring. So, as long as we've got the right material here, it will move or be forced backwards and forwards accordingly every cycle. We have to control that. Now, I'm saying that this solenoid has a maximum frequency of 50 Hertz because of our main supply in the UK. 50 Hertz is what maximum it can do. But in reality, if we were to measure that, is that frequency consistent? We say it is, but how do we know? How do we know that when we plug something in that the frequency isn't 49 Hertz? Or 49.5? Or 30? How do we know? So we've got to think about how accurate is the supply going to be and how consistent is the solenoid going to be. So somebody in your group has got to do a little bit of research. You're going to immediately be thinking, what kind of solenoid can we get for this and how accurate can they be? What can we assume or what can we expect from their performance level? The other thing is, as I think I mentioned on Thursday, I think we want to have a leader designated for the group, and each leader is in charge for 2 weeks. So Monday this afternoon, with the people who are here, the people who are not here, they've missed a golden opportunity to be the leader of a group. So the people are here, you're going to designate one leader for this week and next week. And then there'll be another 2 until we get to week 10, and then the 5th person will be in charge. All right? So try and do that this afternoon. It's going to be important to have that person in charge of the group and to try and control things and make things happen. And I want you in your report to state who was the leader at each stage. So we need a plan, maybe a 10-week plan, and just block out who's in charge for each of these 2 weeks. And I want you to do that this afternoon, without getting into a fight or anything about who's in charge, okay? I'm going to be fairly reasonable about this. So, we've got to get that leader in place. We've got to start doing some research. We've got to find out about the solenoid, what's possible. Now, at the GoTech website, I think that you've been to, it probably won't tell you, in fact I'm pretty certain, it won't tell you what that consistency of output is from the solenoid. Mainly because they're not interested, because they don't have to be that accurate. But we are. So we need to find out about how a solenoid works, how can we control it, what kind of level of quality do we need. So that's a task for somebody in the group to start this afternoon. Is that clear? We also need to start thinking about the other elements in this. the other key elements are spring. If you don't know about springs, now's the time to get somebody in the group thinking, I'm going to be finding out about these springs. What's the quality? How can we control them? Yeah. Have the spring rates from one supplier, are they better controlled than another? Find out about that information and what the parameters are for designing a spring. Because it may turn out that you have to design your own special purpose spring for this application. Maybe it's got a special material because it gives a consistent response. We don't know yet. So someone in the group has to start thinking about that. So that's a couple of tasks. What else might you want to be starting thinking about? What else?
Budget? Is there a budget for that?
A budget?
Yeah.
Well, we haven't defined how much this is going to, any cost limit on this, and the good news is we're not going to put one on it. Because the priority here is that we want top quality and output, regardless of the cost. Remember that this could be potentially saving somebody's life. If it's delivering, say, some chemotherapy to somebody, it's worth paying a lot of money for. So we're not going to put a tight budget on it. The control is going to be in the manufacture and in the quality of everything that makes up this particular device. Now, the other thing that somebody's got to do, if I can remind you of the little graph, yeah. The other thing that somebody, or maybe two people in the group have got to do, is to start getting this data together and to decide what is the relationship between the stroke length, the piston diameter, and the frequency. Let me say that if you remember, I've done this for 1 litre per minute. You want to get half a litre per minute. But we need to know what the basic parameters are. And so each group needs to have a graph like this available to themselves for half a litre per minute. So that you've got the relationship between the stroke length, the piston diameter, and the frequency. But remember, the maximum is 50. And I haven't even drawn it there. But you can put it in if you want, up to 50. Okay? Now it would be very useful if somebody in that group can very quickly put this on a spreadsheet, this information, and get a plot of these relationships, just as I've done. Now that's important because things are going to change. Yeah? Your stroke is going to, you're going to have to change it. You might find later on that it's not precisely enough. You may have to change that stroke length, or you may have to change the diameter. And you need to have this data to be able to recalculate it. Or you may want to change the frequency, and you have to know how things are going to change. You'll also need this equation that is going to dictate the volume output as a function of the stroke and the piston diameter. Okay? So, one or maybe two people in the group could be assigned to do that. And we want to try and do that this afternoon. We need to get the parameters sorted out. Okay? And get everybody working from day one. This is day one if you didn't realise. Alright? Is everybody clear now? We've got to get moving. And the people who aren't here, they're going to be left behind. We just need to press on. Has everybody got that? Now we'll keep coming back to this and to the picture of the solenoid. We'll keep coming back to this because this is going to be our point of reference. Both to understand how it works and to see what the variables could be. Yep.
So are we sticking to the design in the picture?
Yes. That's
And
the
we
concept
only
of
play
using.
with the materials, with the tolerances, that's all.
Yes, you've got to think about the tolerances, and you've got to think about the quality of the manufacture. Yep. The material.
But the places where the springs are, there has to be a spring there.
Yes. Yes. Unless, of course, you come up with a radical improvement with this, perhaps maybe some of these things are redundant. But I think that's unlikely, but you might do. I'm not going to close the opportunity to that. But it has to work in this way. It has to work on the basis of the piston moving as a function of the solenoid operating it. If you, maybe you can come up with a way of that happening without a spring being there, but nobody has done so far. But that's not to say it's not, not missing something. All right? Yep.
So the methods that we have learned in the term 1 of assembly and robust design, they have to be deliberately used to solve these issues.
Correct. Correct. So there'll be some people in the class who did the advanced manufacture course in semester 1. You've got a bit of a head start in that area, but a couple of things we're going to have to go over again for the benefit of everybody else who's joined us, so that they understand what the issues are. Right? So we have to keep people on track. But you might find the people who have done the advanced manufacture, they might be designated in the group to look at that area because they know a bit more about it. Okay? But really what we're going to be doing is a lot of the things that we have already discussed in advanced manufacture, we're putting them into practice now. And finding out about what the limitations are of these techniques and what the benefits are. And finding out if they really do deliver on the things that we want. Alright, so on that basis, I'm going to talk about, just to get everybody up to speed on process capability, which we have discussed in class. Hi, this is just a drive hole. I'll go through this fairly quickly because it will hopefully be fairly straightforward. Process capability. What we're doing here is we're thinking about capability of any process, mainly a manufacturing one, but it doesn't have to be. This solenoid piston pump that we are dealing with is a process. Right? It's taking in fluid, pressurizing it, and putting it out. So it's a process, and it's a process that has variability. Yep. The output won't be 100% constant. It has to have some variation. What we want to do is to control that variation, just like we want to do in a manufacturing process, as we'll see in a second. So, every process has variability, but what causes that variability? Well, we can break it up into two areas, one which we call common cause, and one which is an assignable cause. The common cause things are inherent in the process. Things that are there, we can't do anything about them, that's the process, we have to go with it. Others are capable of elimination, an assignable cause. If we can eliminate that area of variability, we improve the quality of the process. Right, that's something to think about with the solenoid. Is there any part of it where there's variability that we could eliminate? So, we've got these two things, and we can measure this process capability by what's called the Process Capability Index, designated CP, and that's calculated as follows. So, basically we've got a tolerance. Here we've got an upper limit, and we've got a lower limit. In our case, the upper limit would be 0.55 litres per minute, yes? And the lower limit is 0.45 litres per minute in our process for the solenoid pump. And we're going to divide that by 6 sigma, and of course sigma is a standard deviation. Everybody familiar with that term? So, we're divided by 6 sigma, and of course you've got to ask me why 6 sigma? Well, 6 sigma because our normal distribution is plus or minus 3 sigma wide. Gives us a whole spread of that distribution. Yeah? So, that's why we divide it by 6 sigma. So, we can get our CP from the difference between the upper and lower limit divided by 6 sigma, or it could be just the tolerance. In our case, the tolerance is plus or minus 0.05 litres per minute. So, that would be the tolerance, and in that case, we would divide that by 3 sigma, because it's half the total range. That, either calculation, is going to give us our process capability. And that's telling us how well does our process deliver that particular tolerance range. Now we could get this if we had say we made 100 of these piston pumps and we put them all on a test and we ran them for a period of time and we monitored the output accurately, then we would know over a period of time what that process capability was, because we could keep a record of the outputs and see how they varied, and we would know what that process capability was going to be. Agreed? But of course, when you're in design, you haven't made it yet, have you? You're designing it. You're trying to design it to do that. It's all very well testing it and then confirming it, but when you're designing it, you've only got a target that you've got to try and achieve. And you've got to try and do that theoretically and then test it to prove it. So, what is that process capability in any given situation? Why am I walking over here? Okay, let's look at an example of this taken from a manufacturer. Let's imagine we've got a component and it's got a 50mm dimension. It's 50mm plus or minus 0.2. So the upper limit of that is 50.2, or the lower limit is 49.8. So the tolerance is plus or minus 0.2 in this case. So, and it's important to note that in general, manufacturing industry, particularly in the UK, work on the basis of having a capability index of 1.3. This is considered reasonably acceptable. And as we'll find out, that one figure of 1.3 represents a quality level of having about 32 out of every million we make not fall within that tolerance band. So let's think about that. If we were manufacturing 1 million of these piston pumps and we were testing them, if we've got a process capability of 1.33, then only 32 out of that million would not meet the specification. Now that's pretty impressive, isn't it? Out of making 1 million, only 32 would be outside that limit that we've defined for it. That's pretty impressive. So that's the kind of target of quality that's generally applied in the UK. Some industries have an even tighter tolerance and tighter requirement for process capability. So for example, if we were making microprocessors, that's set at 2, a process capability of 2, and that represents 0.002 parts in every million that would not be within specification. 0.002 in every million processors. Yeah? So that's a very, very small number, are not going to be within the acceptable range. Now that's important, isn't it? Because the last thing you want are processors that are taking the next manned mission to Mars to fail on that journey, or not to operate within specification. They have to be incredibly reliable. Our question, our interesting question is, what's our process capability? What's the process capability of this pump that we are defining here? We've got an upper and lower limit. We know we're going to define it by 6 sigma. We have to think, what could that upper limit be? What could that process capability be? That's something for you to think about. It might be that it's less than 1.33, or it might be higher. And that's giving you an indication of what the quality expectation is of this solenoid piston pump. Have we seen that? So it gives us a way of checking the capability of any process. Now remember, it could be the process to manufacture a part, it could be the process to push water through a pump, it could be the process to make soap powder, whatever it might be. They all have a different process capability, and we can control that. Alright, so let's just take this example a little bit further. Right, so what we're trying to do here is work out how do we get this parts per million thing. Well, we can calculate that by recalling our standard normal distribution value. Some of you are about to because you did the advanced manufacture. we've got our Z function here, which is X, which is our variable, minus the mean, mu, divided by sigma. That gives us our standard normal variant, as it's called. And if we know what that value is from our normal distribution tables, we can work out what the value of parts per million is going to be. So, here's our example here. This is our equation. I've got 3Cp equals the tolerance over sigma. Of course it's 3 because it was the tolerance over 3 sigma. I've just moved the 3 here. That has to equal Z. That's the same as the standard normal variant. So we've got 3Cp as the tolerance over sigma. So if we look up the value of Z, and if we allow Cp to be 1.3 or 1.33, then Z has to be 3.99. Right? That's the capability that we want here. And if it's 3.99, and we look up our standard normal distribution tables, then we find there we get a value of 0.999968. So, take that away from 1, multiply it by 1,000,000, we get the answer 32. So that's telling us that if we've got a process capability of 1.33, that means 32 parts per million are going to be outside the specification on every million we make. So that's a very capable process. And I guess we're maybe looking for something similar for our piston pump. You imagine you were getting chemotherapy in the hospital. Do you want the pump that is only likely to have 32 failures in a million delivering that to you? Or do you want something where there's 1 in every 10 that's made that's likely to be faulty? Which one do you want feeding the chemical into you? You want the one that's doing it correctly, don't you? And in particular, if you're designing one, you want to design the right one so that people aren't injured or poisoned, that they get the right delivery of medication every time. So that's what you're trying to do here. So that's how we calculate the 32 parts per million. And that gives us a very good indication of what the quality is. Here's the standard normal distribution tables. This is in one of the data sheets that's on Moodle. You'll see there's one that says data sheets. You can look at that. This is there for you. Z equals 3.99 from our example. I can't see it terribly well, but it's here. That gives us the value of the probability. 1 minus that, times a million, 32 parts per million. Okay? Very simple. That's how it's derived. So, we've got to think about what this capability is going to be in our product and how we're going to deal with it. So this whole process of capability can be described as we can see here. We've got an upper and lower limit, and we've got a distribution within that that defines our capability. And that's exactly what we've got with our pump. This value in the middle here is our target. That's our 0.5 litres per minute. The lower limit is 0.45. The upper limit, 0.55. And we want every single piston pump that we make to be able to operate within that range. And of course we want most of them to be bang on target. Every time, every second, every fraction of a second, they've got to be bang on target. So it's very demanding. If we go outside this limit, you can see the tail of the distribution going outside here. Well, in here, these are the ones that are failing. They're not breaking down and falling apart. They're just not performing at the level that we want. That's a failure, isn't it? People tend to think of failures as being things that break and collapse and all that, but that's not the case. It could just be that this particular pump is only delivering here 0.4 litres per minute. To us, that's a failure. So, this is the picture we've got. We might find sometimes that the mean of the parts that we make coincides with the target. Right? Our target is 0.5 litres per minute. If we tested all the pumps that we make, what would be the average output from that? We hope it would be 0.5 litres per minute, but it might not be in every case. So on average, they might coincide, But we might get a situation where they're separated. That we've got an average, obviously, from the ones that we've made, but it's different from what the target is. Maybe our target, as we've said, is 0.5 litres per minute, but the mean might be 0.4999999. Yeah? Could be. So they could be offset by a certain amount. This could happen, but it could be equally acceptable. The distribution is still within their limits. It's just skewed from the target. So we've got to think about that, and how do we deal with it? Well, in this particular case, we need a different measure for the CP. In this case, we've got the CPK. And we calculate that by subtracting the LO here, which is the limit nearest to the mean, from the mean, and divide it by 3 sigma. In this case, what is the limit nearest to the mean? Sorry, did somebody say something? No? So we're going to get the limit that's nearest to the mean. Yeah, in this particular case. So we need to know what the target is and what the mean value is. And what's the limit closest to that? Because it's shifted one way or it's shifted the other from the target. Yeah. So because it's shifted this way, then this limit would be the one closest, because it's shifted in that direction. So in that case, we would take this value to put it here. But it could be shifted the other way, in which case we take the limit to which it's shifted to. Yeah? So it's just trying to compensate for this idea that the target doesn't coincide with the mean. And that gives us a slightly different value for this process capability. Now, of course, we have to decide, when do we do that? When do we use one and when do we use the other? There has to be a decision point. So let's look at another example to think about this. Let's imagine we've got a tubular component. That could be a piston. Yeah, this is a tubular component, the piston is going inside. So let's imagine we've got a tubular component and it's manufactured at a rate of 25,000 a year. We want to control the internal diameter. It's got a value of 50 plus or minus 0.05. We're going to measure 50 components and to see how well we can manufacture this particular component. So here we are, we've got a record of it. We found that we've made 2 of them had this value, 49.95, 10 had this value, and 1 had that value, and so on. We've got the record of the various values that we've measured. So the mean value in this distribution, on this list, comes out to be 49.98. It's not 50. Right? The target is 50. The mean of this is 49.98. So they're not the same. Does everybody see what we're trying to do here? We've got a target that we want to achieve, but the ones we're manufacturing, on average, are slightly off target. And it's also got a standard deviation of 0.0162. So that's our spread, but we're off target. What do we do? How do we know what the process capability is here? Okay, let's do the calculation. The first thing to point out is that by what extent is the value that we're getting, the mean, how much is that shifted from the target, 50? In this case, the difference is equal to 1.2 times sigma. We calculated the standard deviation in the previous one, which was 0.0162 or something. So the difference between 49.98 and 50 is about 1.2 times sigma. Now the usual convention is that if the shift is less than 1.5 sigma, then you use CP to do the calculation, because that's judged to be a very small separation. So we use CP as the best figure to use. If it's beyond 1.5, then CPK is the way that we calculate it. And it's important to remember that distinction. So let's just check it. Here, we're going to calculate CP. The tolerance is 0.05, plus or minus 0.05. We divide that by 3 sigma. Remember, we calculated the standard deviation to be 0.0162. So in this case, the process capability is looking like 1.03. is that acceptable? It's less than 1.33, right? So it's more than 32 parts per million are going to fail. But also let's check CPK. I just did this just for the sake of it. It comes out to be 0.62. That would then, because it's within that limit, would be giving us an unrealistically low value. So CP is the one we want to use here. And if we went with this particular design and with this particular manufacturer, then I calculate that the CP would result in 1,000 parts per million failing, or being outside their acceptable range. If we take the CPK value, it's about 31,500 parts per million. Now that's a very different prospect to 32 parts per million, isn't it? Which one do you want for the pump that's delivering chemotherapy to you when you're ill? Do you want the one that's got the capability of 1,000 parts per million that could fail? Or do you want the one with 32 parts per million that could fail?
Neither.
What do you want then?
Neither.
What would you want?
Higher than 1.33 CP.
How high would you want it to go?
As long as it's less than 100 parts per million. Realistic.
You want it to go less than 100 parts per million?
Yeah.
And hope that you don't get that
Yeah.
that 100.
Looks like good odds.
Yeah, I mean, we're joking about this, but this is the reality. Yeah? This is the reality. You could be that one person who suffers because the quality of the product that's delivering this isn't good enough for you on that day. Yeah?
You can test it later, right? If it's 100 parts which are not right, then you can have a testing process which removes those 100 parts.
That's another matter. We'll be coming on to that. Yeah, he's made a good point. He's saying although we could design it, or the manufacturing process could result in maybe 100 or 32 parts in every million failing, what he's saying is you could introduce a test that could identify them before you ship them away. Yeah? Now that test, of course, would have to be done on every single one, wouldn't it? Yeah? And you'd have to hope that by testing it, you don't damage it. Wouldn't you?
No, it will slow the production.
It could slow the production, increase your costs. I know you mentioned costs. That could happen. But he's on to something here, isn't it? Because it's a way that we recognise that we could maybe eliminate those poorer quality products if only we could test every single one of them without, by testing them, destroying them or weakening them in some way. We'll come back to that point. It's a very good one. So hold on to that in your mind about how we might do that. But this is giving us a figure that we're starting to aim at. And one of the things you're going to have to do in your groups is to decide what is that process capability going to be. We know we've got our limits, so how accurately and to what level of quality do we need to make this product? And by starting to think about that, other design decisions fall into place because you know what the target is. You know what you've got to try and achieve. And then it'll become easier to apply tolerances to other things, to decide what the quality of other components have to be. Yeah. So, hopefully you're all going to see, which is why this is called integrated engineering design. Why all these things come together. Yeah. All these things that you previously maybe thought about separately, all suddenly have to be considered together. Okay? Right, I just want to finish this little bit. I wish I had a pen. Excuse me a second, I put those on.